Thank you. You'll have to deal with my voice a little bit today. My allergies have been acting up, so if I sound hoarse, my apologies. If I go too fast or if you have any questions, please let me know and I will take care of it. And I'm going to turn the Wi-Fi off so I don't get bothered. Okay, so we're going to talk about asynchronous programming. My name is Sean McCune, and I'm with the Big Nerd Ranch. And feel free to grab me sometime during the next 2 days if you have any questions on anything we talk about. So what is asynchronous programming? Well, it's small units of code run on separate threads, or it's small units of code that you run on the same thread, much like running a block on the main dispatch queue in Grand Central in iOS. C# implements asynchronicity via the async and await mechanism, which we'll be covering in just a few slides. And it allows units of code to be scheduled efficiently for both optimizing performance and resource usage. So what are we going to talk about in this talk? Well, we're going to cover the async await mechanism. We're going to compare a little bit with iOS concurrency. We'll take a look at how we run tasks on other threads. We'll look at an example, and then we'll cover how to cancel a long-running asynchronous operation, what happens if your asynchronous operation throws an exception, how to wait on tasks to complete, how to use tasks to delay the operation of something, how to do a little bit of cooperative concurrency with yield, and how does asynchronous programming affect the UI. So let's take a look at the async and await mechanism. You implement asynchronicity with the async keyword by declaring a method to be asynchronous. And by convention, your asynchronous methods should end with the suffix async. With one exception, is if you're going to make a method that's automatically generated by Visual Studio asynchronous, well, most people don't go in and change the name to add that suffix. You just add the async keyword and you've made the method asynchronous. Asynchronous methods cannot take ref or out parameters, and they return before completing their asynchronous operation to the caller. And an asynchronous method should have one or more await expressions specifying asynchronous tasks to perform. And if you don't, the compiler will warn you. It's not an error, but the compiler will warn you, because if you don't have an await expression, which is where the asynchronous operation gets kicked off, there's really no point in having an asynchronous method. And you can also make lambdas and anonymous methods asynchronous. So an asynchronous method also can only have a couple different return types. If no information needs to be returned to the calling method, then you just return void. But if you need to return state information about the asynchronous operation, like has it completed yet? Is it in the process of being canceled? Has a cancellation in process going on? Then you should return the task, which allows you to get at all that information. On the other hand, if you need state information and some kind of return value from the asynchronous operation that is the result of the asynchronous operation, then you return a task with a result property of the parametric type T. And the return task's state will be updated before being returned, so you don't have to do anything. You can just simply return the task, and you'll see that coming up in a few slides. It's very, very simple. The asynchronicity in Windows 8 is very easy to implement and takes care of a lot of the details for you. So here's an asynchronous method. One quick thing is that in this example, you see the initial calling method there is main. That makes this not a Windows Store application, because this is a console application. In Windows Store apps, you don't have a main. The main is provided for you. But the await and async mechanism is the same in Windows Store apps and in console applications. So I just wanted to point out that this example, for the sake of brevity on this slide, is a console app. But it calls a method doStuffAsync, which you can see there. It returns a task with an integer result property, and it's declared with the async keyword. Now that async keyword is contextual, so if you use it in the signature of a method, that's the async keyword. But you could also have a local variable that's, say, an integer named async, and that's just a variable named async. So it's a contextual keyword. So in the async method there, we do some stuff. We call a method, literally, do some stuff. And then we call this await expression, which runs some code asynchronously. And right there is where the asynchronicity happens. We both return to the calling method right there at that await, and we sit there and wait for the asynchronous method to finish and continue on with the rest of the code. So right at that await expression, we actually split code contexts, and we essentially duplicate the code that's running in that method, and one of them returns to the caller with a task, and another one sits there and waits for the asynchronous method to complete. And we'll go into that in a little bit more detail in a moment. And so basically, to recap, that is that the await expression executes some code asynchronously, and then the await expression waits for it to complete, even though we've also returned to the calling method. The code following the await expression is called the continuation, because the await expression returns to it to continue running after the asynchronous operation is complete. The continuation after the await expression can contain other await expressions and their continuations. So you can stack await continuation, or you can put the await in a loop and just be looping around that same await. The calling method gets returned to as soon as you hit that async operation, the await expression. And then the async method returns the task that is running so that you can query it to see, am I completed? Is it being canceled? Unless the calling method doesn't care. If the calling method doesn't need any information, if it's just a fire and forget of the asynchronous operation, then your asynchronous method can have a void return type. So the calling method will continue then in parallel with the await expression. And if the task's result property is read, the calling method will wait until the task is complete, if it's not already complete. So just by accessing the task's result property, you have a mechanism to synchronize yourself with the end of the asynchronous operation. So let's take a look at the parts. I'm not sure if I turn my head, do you hear me?
Yeah, figure it out.
Okay. Yep, question?
Quick question.
Sure.
You said the calling method will, so you're effectively saying if the calling method checks the task's result method, the calling method blocks.
Calling method blocks,
Okay.
right there.
Thank you.
So the first part in red of this asynchronous method is just normal code, and it runs synchronously. So if do some stuff takes 30 seconds, and you run this asynchronous method from your main thread, your UI thread, you will take 30 seconds where you've locked up your UI. So that's not a good idea. But you should only have short running code that runs synchronously before the first await. As soon as you hit that first await, we're going to run that code in purple asynchronously. And I don't know how many of you guys are Unix developers, but one of the ways that I've thought of this is I compare the await almost to a Unix fork. You know, if you're familiar with fork, it duplicates your process. Everything's exactly the same. Your variables have the same value, etc. And the only difference is the system call fork returns one value to the original process, letting it know that it's the parent process. It returns a different value to the child process, letting it know that it's the child process, and they can go off and do different things from that point. Well, what happens here in the await, you can think of, it's not exactly what's going on, but you can think of it as not a process duplication, not even a thread duplication, but kind of a code context duplication, where this method is duplicated and they both are sitting there at that await expression. the parent one, the one that's actually been called by the calling routine, that one returns immediately to the calling routine with whatever the result of that await expression is, which in this case, task.run is going to return a task. The other context is going to sit there and actually wait for the asynchronous operation to complete. And as soon as it completes, it's going to return the result of the asynchronous operation to the code in green there, which is the continuation. And it's going to continue running the code in green. And when you get down to the bottom and you see that return value there, that return value, where does it get returned to? We've already returned to the calling method in the other code context. Well, a stub of code gets generated that will be returned to by this code that takes that result value, stuffs it in the result property of the task. And so at that point, back in your calling thread, your calling method might be looping around, waiting for that task to be completed. When it is, it can then look at that result. Or it may have just tried to access that result, in which case it would be blocking, waiting for that result to get set and the task to be set to completed. So, and you also notice that the asynchronous method has a return type of task with a task with an integer result property, but we're returning an integer in the continuation. Well, that return value in the signature, that's the value that gets returned to the calling code. And that's the value that's returned by the await, which is what task.run returns, which is a task. So that's the return value to the calling method. The return down at the bottom of the method is what gets returned to that stub of code, which is the integer that will be the result property of the task. Mm-hmm. Oh, sorry, that's a typo. Yeah, that would be result 2 or something, maybe a combination of result 2 and 1. Yes, I was combining some code from different examples and had a typo. Sorry about that. But thanks, I'll make a note to fix that. Anything else? Yes?
How does the parents who called this method know this task been done?
How does it know when it's done?
Yeah, do they have notification say, hey, I'm done?
Yeah, actually it's simpler than that, and you'll see an example in a moment, but the task object has a property called isCompleted. And so you can just check that, and it will be true or false, and that will let you know if it's completed or not. And also you can just try and access the result property if it has one. No, because the continuation is your completion. It's what happens after the asynchronous code is done. You don't need to have a separate block. That's one of the cool things about asynchronous programming in Windows 8. It lets you write code that looks like you're writing linear code, but the stuff before the asynchronous code, the red stuff, that runs synchronously, and everything in the purple and green runs asynchronously, and the green part, the continuation, doesn't run until the actual asynchronous code in purple is done. So the green continuation acts as your completion block. Yes, way in the back.
So memory management, when it comes to blocks and things like that, you got to be careful, and also with threads. How does that affect? What do you have to be careful about when you're touching memory and allocating memory in various inside, I guess, tasks and outside and all that kind of stuff?
You don't. It's generally taken care of for you. Obviously, because you have two pieces of code running concurrently, you don't want to try and destroy an object, in one code context while the other one's, running asynchronously with it. But you generally don't do that anyway. You're not really taking care of the memory management and explicitly destroying things. It's garbage collected. As long as you have references, to the objects, they're going to stay alive. I don't know if Jaime wants to jump in. You look like you're. Oh, okay. So you don't really need to worry about it any more than you would in C# under any other circumstance.
then it's only alive, that memory that you allocate is only alive while the task is running.
Yes, that's true, because yeah, it's just like any other object that you would allocate. It's alive during its scope, and unless you somehow pass that reference off to some other piece of code, it will only live as long as the asynchronous task is living.
Maybe jumping ahead, but so assuming do stuff async is called from the main UI thread, and I would assume then the await task run, I guess the second time do some stuff is called, runs in a second thread.
Yeah, that is coming up, but I think I should maybe cover a little bit of that now. The await expression, whatever it is, does not run in another thread. It's actually a bit of code that's scheduled to run on the current thread, the main thread, in the future. It's like putting a block on the main dispatch queue. Okay. However, what this particular bit of code is doing is when that bit of code runs on the main dispatch queue, it's going to run a task on another thread. And so if you want to run something on another thread, you do it by doing a task.run in your await expression. Okay, so that's, and we'll get into that in more detail in a few slides. Yeah.
So one of the very common patterns we have with GCD, for example, is that you fire off a whole bunch of blocks, and then you've got the dispatch groups mechanism to capture the fact that they've all been finished and terminated, and then you can now go and do
Right.
something. So start a bunch of downloads, and then when it's done, now go do something. How would you capture stuff like that?
Can I cover that in a little bit, or at least cover bits of code that might answer your question? Okay. Yeah, that one, there wasn't the mic there. So the await expression waits on something that is an awaitable object. And they're an object that has, this is under the hood stuff, but it's interesting. It has a method that's called a getAwaiter that returns something that is an awaiter. And the awaiter runs synchronously on the calling thread, like I just explained. That's like running something on the main dispatch queue, unless you do something to then run code in another thread, which is what running a task does. Normally, you just use a task. That covers 95% of the cases. You don't normally have to roll your own custom object. So that's just a little bit of under the hood stuff of how that await mechanism works. But normally you just await task.run something. And the awaiters have the following methods. You can check and see if they're completed. You have an action handler, and one of the two get result methods. And tasks have all that, so that's how they are used as an awaiter. So I'm going to compare this a little bit with iOS concurrency, and hopefully that will answer your last question there about how do you handle kicking off multiple tasks and controlling them. So in GCD, we have the main dispatch queue. Well, using async await is pretty much the moral equivalent of running a block asynchronously on the main thread. There are also concurrent queues where you're going to run tasks on another thread while using the await expression to specifically run a task on another thread gives you pretty much the same effect as concurrent queues in GCD.
Processes that are spawned are serially executed, no priority, no high, medium, sort of thing?
Yeah,
The priority of these is serially executed in the queue, main queue, or there are some priority associated with each that you can assign?
They are run on the main thread, but I don't believe there's any priority because they're not running in another thread. They're just code that's scheduled to run on the main thread, kind of like more like a run loop. Okay, and so they're going to run once your main asynchronous call is done, and the main thread is doing something, and you get into
It's
a point where you give the other code in the run loop a chance to run, then it will run, and then run your code in another task. Now the task has some abilities to run in another. Do you know what the priority setting of the tasks are when you run them? Yeah, there's no queue, but if you have multiple threads, if you kick off multiple tasks in multiple threads, is there a way to adjust the priority of some of them?
For some of the tasks, like if you dispatch if you use the dispatcher run async, which is different than tasks, you can do priorities.
Okay.
For everything else, we have one thread pool. So if you do dispatcher.run async, then at that point we have priorities that will matter. If you do just standard tasks, we have one thread pool and they all run at the same.
Okay. Yeah, I had not seen anything where you could adjust those priorities explicitly. So let's take a look at how you run these tasks in another thread, because there are several different ways. They're very similar. In fact, most of them are special cases of the others. You can use one of these for run methods. You can either run an action delegate, which is essentially just a piece of code. You can run a func object that returns some kind of result type. And then a specialization is a func object that returns a task, or a func that returns a task that has a particular result type. And this is where we get into how you control multiple tasks that you've kicked off. So an action delegate, and did you explain delegates? Because I wasn't able to hear.
Yeah.
Okay. So an action delegate encapsulates a method that has no parameters and returns void. And so if you look at the bottom in the asynchronous method there, in our await expression, we're running a task which is a lambda that has no parameters, and it's calling debug writeLine, which returns void. So that lambda that we're running in another task that calls debug writeLine is an action delegate. And it will just simply run that debug writeLine code in another thread. In this case, the code that we're running in another thread is the lambda that calls the method myTask, which returns an integer. So that's a func object that has an integer result type. So that's not an action delegate. And that's where you can return a value to the await expression, which will then be the integer result property of the task that gets returned to the main thread, or the calling routine. And the next specialization is a func that returns a task. And this is a case where you're using one thread to kick off a bunch of other threads, and you can handle them that way. And then there's methods to synchronize, even in your asynchronous operation, waiting for one or all of those threads to complete, before you continue on. And we'll cover that in a little bit. And then the final one is where you're returning a func object that returns a task that has an integer result, or some type of result property. And so that's just a special case of the last one. So let's look at a real example. Let's say you have to calculate a Fibonacci algorithm. That's a very common thing you have to do as a software developer, I'm sure, in all your mobile applications. And let's say that we're really bad developers. And so we implement a really bad version of the Fibonacci algorithm that's going to be very inefficient and take a long time. And instead of deciding to fix your algorithm, you decide you're just going to run it in the background so that maybe people won't notice that it's going to take as long of a time. So I have this Fibonacci algorithm that's synchronous. It's recursive, but it's synchronous. And I'm just going to wrap it in another method that just calls it asynchronously. And the value will be returned to the method and returned to the calling method through the result property of the task. And that's basically recapping what I just said. The async keyword makes the calculate Fibonacci async method an asynchronous method, and the await expression specifies the operation to run, which in this case is our lambda that calls calculate Fibonacci synchronously. So here's an example of calling that. We simply call it, and we can loop around in that while loop, checking to see if the task has completed. Any questions on that? Okay. So what happens if you have a long-running task and you need to cancel it? And what happens if your long-running task has some errors and is going to throw some exceptions? You're operating off asynchronously. Who do you throw the exception to? And how do you catch it? Well, canceling an async method is a cooperative process. You need to create a cancellation token source object, get its cancellation token, and then pass that cancellation token into your async method because it's going to need it to find out if it's being canceled. And then anytime your calling method wants to cancel the operation, it just calls the cancellation token source's cancel method. And I say cancel an awful lot in that slide. So your asynchronous code needs to cooperate with that. It's going to have the cancellation token passed in. It's going to check its is cancellation requested property every so often, based on whatever your asynchronous code is doing. Hopefully it will have the opportunity to do so. If it's true, then you just need to do whatever you need to do to clean up and end your operation. So here's an example. The calling routine, you create your cancellation token source, get its cancellation token, kick off a couple of Fibonacci async calculations. Notice I've had to modify it to pass in the cancellation token. We're looping around in a while loop, waiting for the async operation is going to finish sooner to complete, and then we'll cancel the operations, which if both were still running, they would both be canceled. But the second one is already completed based on this code. But the first one will be canceled at this point. And we can take a quick look at the async code. Now it takes that cancellation token. I'm periodically checking it. I check it before calling the synchronous version of the Fibonacci algorithm, and I check it afterwards. But I also pass the token into the synchronous routine because I'm going to check it every so often, before the recursive calls and after the recursive calls. If I was a better programmer, I would split up those two recursive calls into two separate expressions, assign variables to the results of both, and check the cancellation token in between the two recursive calls so that we could maybe hit the cancellation a little sooner if it occurs. And I'd also put the second recursive call, I would make that happen first because that one will take less time. But this code is so bad for purposes of example that there's no point. What about exceptions? The await expression can be encapsulated in a try-catch block, and exceptions thrown within your asynchronous code will be thrown across the await boundary, and you can catch them in your other code. Any questions? Yeah.
So just to be clear, like iOS,
Just to be clear, like iOS, there's no timeout. So if you were doing this thing could go forever, and if you want to get some timeout value, you have to put that in there in the same place you're checking to see if the thing is completed, right?
Yes, and we'll see in a little bit, there are some methods to synchronize on the completion of tasks that lets you specify a timeout. Okay, so if you're waiting on a task or tasks to complete, you do have the ability to set a timeout. But the cancellation method or the cancellation procedure here is not for, there's no timeout associated with it. It's purely cooperative. You're just saying, hey, cancel yourself, and your asynchronous code has to know to check that, and you just have to be able to get to it periodically. And so you should try to write your code in such a way that you have that opportunity. Don't necessarily just do something that will block, waiting for some kind of I/O or something. And we're actually going to get to that right now. On waiting for tasks to complete and using tasks to delay operation of other code. if you need to wait for tasks to complete, you can either just call the wait method, or you can pass in an array of tasks that you want to wait for all of them to complete or any one of them to complete. And you can see they have a number of different signatures there. The first one, you can pass in an array of tasks, or you can just pass in the tasks separately, task 1, comma, task 2, comma, task 3, and they'll be gathered up into an array automatically for you. You also have signatures that allow you to specify a millisecond timeout, or use a cancellation token to cancel the waiting. You can pass in a time span object as a timeout, and one that also lets you specify both a timeout and a cancellation token. So you can basically interrupt your wait as often as you want. Yes?
Can you call these async methods on secondary threads, and can you set up the scheduler on secondary threads, or is it only the main thread that can be run on?
You could call an asynchronous method from anywhere, and the await mechanism will run its expression on that thread that you're in,
Right.
and then if you use task.run as your await expression, you're just going to be kicking something off in yet another thread.
Okay, thanks.
Mm-hmm. Anything else? Mm-hmm.
I'm curious, in the Visual Studio environment, is there anything novel, new, or different or creative for debugging asynchronous processing versus coming from an Xcode environment? Since you've seen both, you've seen both sides of the black hole.
Yeah, I don't know that novel or any of the other adjectives you use apply. I mean, you can debug your code, and you can inspect variables. Right. Mm-hmm. Right. So I mean, you can basically debug everything you need to debug. There's not some separate UI that pops up that lets you do something different. It's very much they've really encapsulated and abstracted away a lot of the worry about dealing with threads and asynchronous code. So you can do what you need to do. Really, it just works. And wait any has similar signatures as wait all. You can also, in your asynchronous code, you can await for tasks to complete, when all of your tasks complete or when any of your tasks complete. And that will, in your asynchronous code, sit there and wait for that to complete before running the continuation that comes after those awaits. So it's very flexible in that way. So you can wait for tasks either in your calling routines or in your asynchronous routines. And that allows you to do something like this, where you can call task delay and pass in a timeout value or a delay value. And so if you pass in 5,000 milliseconds into that first task delay, your asynchronous method is going to sit there for 5 seconds before returning and running that awaits continuation. And so that's a way that you can use to put your code that you want to run in the continuation, but you don't want to run it for like 5 or 10 seconds. You can use an await delay right before that and delay the operation. But as soon as you hit that await, you will return to your calling method. So you're doing that all asynchronously. You're not holding up the UI or your main thread. So let's take a look at some cooperative concurrency using yield. The task static method yield returns immediately. Both the call returns to the calling method like normal asynchronous method does, but also the continuation, that it essentially is going to return immediately, which means that the continuation will be immediately put on the quote run loop to run at the next earliest convenient time. And so that's essentially the degenerate case of calling task.delay with a value of 0. And so what it does is if you have 5 or 10 or 1,000 asynchronous operations going on, and they're all long running, they can, within themselves, be occasionally calling yield to ensure that each one of those threads is getting an appropriate amount of time every so often to execute, rather than maybe one's hogging it up more. You don't want to kind of get into a degenerate case where you have 10 different threads running and one of them is running almost to completion before the next one gets a chance to run, where it runs almost to completion before the next one gets a chance to run. And so if you really have that kind of long-running threads, and you really need to make sure that they're all getting their time slices every so often, you can cooperatively yield to the others. So here's an example. We kick off 3 asynchronous Fibonacci calculations, and we spin around in a loop for a while, and then we wait for them all to finish. The yields are in the asynchronous method. Here I've rewritten the Fibonacci algorithm to no longer be recursive, so it'll be much faster, but it's in a loop, and I want to make sure that they all get a chance to run concurrently. And so every so often, once every 10 times through the loop, that thread is going to yield itself, which will put its continuation, which is in this case another run through the loop, on the thread to be run in the future, allowing one of the other threads to pick up and start running. Doesn't create another thread. It just is rescheduling blocks of code to run on the one they're already on. Any questions? Okay, so how does asynchronous programming affect the user interface? Well, just like with iOS, the UI runs in the main thread, and if you do something that takes a long time, you will lock up the user interface, and you will not have happy users. So here's an example of some bad UI synchronicity. What the user, or the developer in this case, is trying to do here is he has a button that normally says waste some time, and when you click it, he wants to disable that button, clear some text block, and change the button's text to say wasting time. And then he wants to run this long-running Fibonacci algorithm. And then when it's done, he wants to set the button to be enabled again, put a result value in the text block, and change the button's text back to normal. The problem with this is all running on the main thread. So when you set those things at the beginning of the method, setting the button disabled and so forth, and then run the Fibonacci algorithm, the UI doesn't get a chance to run. It's not going to update itself at that point, so the user's not going to see the button be disabled while the Fibonacci's algorithm is running. And the whole rest of the UI is going to be locked up as well. You can sit there and try and hit any button or control that you want, and nothing will happen. And then the Fibonacci algorithm will end, and you'll set the enabled flag back to true again, and the other things, and then the UI gets the chance to redraw itself when we return from this method. And the user will have seen nothing change, really, other than he'll see the result written into the text block. But other than that, the user will have seen nothing happen except the UI lock up. And so that's not what you really want. Here's what you really want, except I'm not going to run the Fibonacci algorithm here. You're going to do that in one of the exercises. But in this example, we set the button to be disabled and do the other changes to the UI. And then we asynchronously delay for 5 seconds. And when we hit that await, we immediately return to the caller, which allows the UI to run. So the UI will immediately redraw itself, the button will be disabled, everything else on the screen will still be active, and in 5 seconds, the continuation will run and set everything back, enable the button, set the button's text back to normal, and write something into the text block. And what made this possible was, if you look back at the bad version, look at the signature of the button handler there. It's private void, waste time button click. In the good version, It's private async void. So I made the button handler, whether you entered it by hand or generated it using the Visual Studio Designer. If you just add the async there, you've made that method async. That lets the await work, and that lets you not lock up the UI. Yet, you still have written a button handler that looks like linear code. You do some stuff before you do your long operation. You do your operation, the real heart of what you want to have happen when you click the button, and then you set everything back again in the UI. And so it looks like you're writing linear code here, but you're not. You can also, if you like to write your button handlers and your other UI handler, event handlers, in code in your initialize routine, I don't know if probably you've gotten to that yet because of the order we're doing some of these talks. But instead of doing it in the designer, if you want to put the code in your initialize routine, you can do so. We have a button called SomeButton. It has a click handler. We're adding the event handler right there in line. It's a lambda, but we're declaring it as async. And so it lets you put your code right with your event handler, right with the click. It's all in one place. You don't have to write a method, put it somewhere in your file, and then in your initialize routine say SomeButton.click plus equals that method. You put the code right there. It's all in one place. You can see it. You don't have to hunt through different places in the code to find it. Any questions? Because that's it. Yeah?
So how do you run a task on a particular thread? Let's say you have a thread particular for networking, just go and fetching the data. How do you just say, hey, I want to fetch data from server, just run these things on that thread?
You don't really control what particular thread that you're running on. You just say task.run. You're going to run on a thread. I don't think there's any way that you can specify what thread to run on, is there? Yeah, that's not the model.
So let's say you use test run to run in a different thread. At the end, how do you return to the main thread to update the UI?
How do you return? So could you repeat that question again?
Yeah, let's use task.run to run a long task in a different thread.
Okay.
At the end, I want to update the UI. How do I do that?
Okay. Let me find a good example there. No, I'll go back to that one. So here you kick off a task in another thread. When it returns, in your continuation, you could re-enable buttons or do whatever you want, update a UI with some values, just like at the end where I had the slide with the UI, where we're doing the exact same thing. After the await expression, in the continuation, we're fiddling with the UI. So you can do that. Mm-hmm.
So let's say I'm on a page,
Mm-hmm.
and then while I'm running this task, I'm clicking back, go back
Yep.
to the previous page.
Okay.
Then what happens?
So,
Well, you've kicked off something that's running in another task, so that task is still there. If your page doesn't, I mean, this is something you would have to structure in your code. If your page still exists but isn't being displayed, there's still code there that the UI can be fiddled with, but the user won't see it because it's not being displayed. But if your page is actually gone, well, then you can't do that. And so you'd have to know, you'd have to know your code to know that when I do this operation, this page goes away, so I can't access it. any more.
Let me make a couple comments just to
Sure.
make sure we are on the same page.
Yeah,
So,
so to speak.
you're looking at it on C#, and what you're looking at here is some compiler magic, right? So your question is, hey, if I'm in the UI thread and I launch a task, how do I get back to that UI thread? And the short answer is the compiler does all that for you. So there's magic behind it where literally, we're kicking off the thread, we're sending off the work, and then the compiler goes in there and splits this method into multiple things. So for example, if you're looking at that, what he has on the screen right now, that's actually going to get split into two different methods. One of them that's going to be called before the await, and then one that gets called after the await. So to your question about, hey, if I kick from the UI thread and I do something, how do I get back to it? And the answer is you'll always come back to the thread that you started on. So if you're in the UI thread, you kick a background work, you kicked an await, you're going to come back to that thread. Now, if you're somewhere, for example, like if you're an accelerometer, and the accelerometers by default fire on a background thread, they don't fire on the UI thread. And at that point, you're thinking, okay, now I'm on a background thread, and I didn't even kick it off because the accelerometer did the work. We do have something, the UI thread has this thing called a dispatcher. And you can get a hold of that object from your window, and just say, hey, I'm in a background thread, but I have a hold of my object, a dispatcher, and then I can just say dispatcher.run, and that automatically sends you back to the UI thread. So to your question about, hey, how do I get back to the UI thread? The dispatcher object can get you back from anywhere. You just have to have a reference to that. And then I want to make one more comment that, because these are, I don't think you're seeing these, and it just comes down to order and certain things. We wanted to get the foundations, and async, we thought it was almost a foundational language thing. But I want to throw these out there so you understand why async is so important. On Windows runtime, so on the Windows RT, where all of our APIs are, I would say, well, we have a rule that says any API that takes 50 milliseconds or more is going to be asynchronous. Right? So by default, when you're calling onto the Windows runtime APIs, so you're going to be doing a lot less of your own create threads, even though you're still going to use it. So await and task.run is going to help you a lot. But in our world, a lot of our APIs are already asynchronous. So if you're making a network call, you don't have to create your own thread, then make the network call, then return. Right? You're going to be calling a network API that's going to be asynchronous to begin with. So literally, I wouldn't say the APIs are I wouldn't give you a percentage of the APIs that are asynchronous, but I can tell you that there's a set rule from a design standpoint that says, can this API take 50 milliseconds or more? And if the answer is yes, then we made it asynchronous to begin with, right? So for example, you're going to see this when you go in there and look at file APIs, right? Opening a file, reading a file, all these things are asynchronous already. Network APIs, same thing, right? So you're going to be doing a lot less of, kicking off your own tasks, but you do have to understand then, and I'm sure, at some point your own apps are going to do asynchronous work. So that's just relevant for you to kind of follow. So.
And you'll see that later on today, even in the web services section that I'll be doing, where it's all their APIs are asynchronous.
So this is a related question, and you may have already answered it. I think you have, but I just want to make sure that it's clear. In iOS, if you do updates on the user experience from a background thread, you're asking for crashes and horrible things to happen. So let's take the example of I have a background thread doing communications, and I'm trying to update a user experience element based on that. So what you're saying is I get a reference to, what was it? To the dispatcher, and from my background thread, I can say, hey, we're now at 60%, and it updates a graph, and then I get back to my thread, and it works. Great, thank you.
And also remember that, like in this example, when you come back to the continuation here, it's not necessarily that continuation is running in that other thread. That may be running on the main thread.
But the continuation isn't getting called multiple times, because that's what you're doing with the progress. It's, you're 10, 15, 20.
Right.
So the continuation is run once, or it's run multiple times.
The continuation runs once for the await. But if you're running multiple awaits where you're asynchronous operate, okay, what you're saying is you have a long-running asynchronous operation, and you want to update the UI from within that asynchronous operation multiple times. Okay, yes, yeah, in that case, yes.
Okay, thank you.
Here. So you talked about using tasks and things like that. Are there mechanisms there for semaphores and locking, access to variables between these various threads so we don't end up clobbering over things? I assume there are, but
Yeah, but they're not usually needed with this mechanism. I think I'll let Jaime mention any of those more.
well, like for example, if I have a variable and it's multiple threads could be writing to it, I assume there's some way I need to factor
There's
it out.
synchronization mechanisms, yes.
Yeah, we definitely have everything you need, a lock, readers and everything else. We have lock and the mechanisms that you would need to synchronize access to your variables so that you can make it thread safe. We also document pretty well on all of our APIs. When you look at the documentation, you can see what's thread safe and what's not. So from a design standpoint, we go back and tell you, hey, this method is not thread safe or this method is. In particular for static methods that tend to matter because everything else you kind of have control over your own objects. But when the method's static, we tend to tell you, hey, this method is not thread safe. Yeah, that's it.
Yeah, we didn't cover all of those things because the stuff that we did cover we think is foundational for the rest of the Windows API that we're going to be covering, both such as the web services and even the UI, so that you can know what's happening when you see these Windows API calls that are all asynchronous. But yeah, there's a whole lot more under the hood that you can get into. Is that it? Thank you very much.